Right now, 126 million miles from Earth, something extraordinary just happened. A visitor from another star system reached its closest point to our Sun yesterday, and scientists watching from Earth witnessed something unprecedented: the real-time decomposition of matter from beyond our cosmic neighborhood. This object, designated 3I Atlas, is now racing away from the Sun at 58 kilometers per second. That's more than 130,000 miles per hour. To put that in perspective, if you could drive that fast, you'd circle the entire Earth in about 11 minutes. Yesterday, October 29, 2025, at precisely 11:44 Universal Time, it reached Perihelion, its closest approach to our Sun, and in those moments of peak solar radiation, this comet from another star system shed its frozen guts across millions of miles of space. It carries with it ice forged in the disk of an alien star, molecules that condensed in conditions we can only imagine, and potentially the chemical fingerprints of a planetary system we'll never see. Now, as it begins its outbound journey back to interstellar space, the brief window for studying this messenger from the cosmos is rapidly closing. The story begins on July 1, 2025, when the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, detected an anomaly. The automated survey telescope, designed to scan the night sky for potentially hazardous asteroids, flagged an object moving through the constellation at 4.5 astronomical units from the Sun, just inside Jupiter's orbit. At first glance, it seemed unremarkable. The solar system is full of icy bodies making their long journeys around the Sun, but then astronomers calculated its trajectory. The numbers didn't add up. The object wasn't following an elliptical orbit like a normal comet. Its path through space was hyperbolic, which meant it wasn't bound to the Sun's gravity. It was passing through. When researchers plugged the data into their orbital mechanics software, the eccentricity value came back at 6.14. Stop and consider that for a moment. An eccentricity of 1.0 means an object is barely escaping the Sun's gravitational pull, following a parabolic trajectory. Anything above 1.0 is hyperbolic, meaning it's moving too fast to ever return. The previous record holder, Oumuamua, had an eccentricity of 1.199. The second interstellar object, 2I Borisov, discovered in August 2019, had similar numbers. But 3I Atlas? Its eccentricity of 6.14 shattered all previous records. This wasn't just passing through our solar system. This was barreling through at speeds that spoke of a violent ejection from its home system, a cosmic exile traveling the galaxy for possibly millions of years before chance brought it close enough to our Sun for us to notice. Let's back up to what happened before this moment. The concept of interstellar visitors isn't new. Astronomers have long theorized that space between the stars must be teeming with rogue objects, comets and asteroids, and even planets, ejected from their birth systems through gravitational interactions. Computer simulations of planetary system formation suggest that for every object that remains bound to a star, 3 to 100 times as many get ejected into interstellar space. Our own solar system likely expelled countless icy bodies during its chaotic youth when Jupiter and Saturn were still migrating and their gravitational influences were reshaping the architecture of the inner solar system. But detecting these wanderers is extraordinarily difficult. Space is vast beyond human comprehension, and interstellar objects are small and dark. They're visible only during the brief window when they pass close enough to a star for sunlight to illuminate them, or for solar heating to cause outgassing that makes them appear brighter. Before 2017, we had never confirmed the detection of an interstellar interloper, though scientists estimated that several objects of Oumuamua's size pass inside Earth's orbit every year, and that approximately 10,000 are passing inside Neptune's orbit on any given day. We simply couldn't see them. Then came October 19, 2017, when the Pan-STARRS telescope in Hawaii spotted Oumuamua. Its Hawaiian name means a messenger from afar arriving first, and it changed everything. For the first time, we had proof that objects from other star systems do indeed pass through our cosmic neighborhood. What made Oumuamua so puzzling was its lack of visible cometary activity. It showed no tail, no coma of gas and dust. Yet it appeared to be accelerating in a way that couldn't be explained by gravity alone, suggesting some form of outgassing was occurring, just not in detectable amounts. 2 years later, in August 2019, amateur astronomer Gennady Borisov discovered the second interstellar visitor using his custom-built 0.65-meter telescope in Crimea. Unlike Oumuamua, 2I Borisov looked and behaved like a typical comet from our own solar system, with a visible tail and spectroscopic signatures showing it contained water, carbon monoxide, and other familiar volatiles. It reassured scientists that some aspects of comet formation might be universal. Here's where it gets interesting. Comet 3I, Atlas, is neither Oumuamua nor Borisov. It's exhibiting what scientists describe as hybrid behavior. Unlike Oumuamua, which showed no visible outgassing, 3II Atlas is actively vaporizing as it approaches the Sun. NASA confirmed that the Hubble Space Telescope has captured rare, high-resolution images of the comet shedding dust and ice as it journeys sunward. The observations reveal a brilliant dust plume and extended tail, clear evidence that the comet's frozen core is sublimating under increasing solar radiation. Think about what that means. This chunk of ice and rock, forged in the protoplanetary disk of a star we can't identify, possibly light-years away, has been drifting through the cold darkness of interstellar space for potentially millions of years, at temperatures barely above absolute zero. Now it's encountering our Sun, and that encounter is causing it to react, to change, to literally come apart. But here's the thing. Unlike Borisov, which resembled a typical solar system comet in its behavior and composition, 3II Atlas is showing unusually intense volatile activity. The rate at which it's losing mass is noteworthy. NASA's data shows a steady decrease in the comet's overall brightness, a clear sign that it's rapidly losing material during its solar pass. It has a stable hyperbolic trajectory that will carry it back into interstellar space once it rounds the Sun, yet its outgassing behavior is surprisingly vigorous for an object that should have lost most of its volatile surface layers during eons of exposure to cosmic radiation in interstellar space. Scientists studying this phenomenon are particularly fascinated by 3I Atlas because, unlike comets from our own solar system, its chemical fingerprint may reflect conditions in another star system. Every solar system forms from a protoplanetary disk with its own unique chemical composition determined by the metallicity of the parent star, the distance from the galactic center, the presence of nearby supernova that could have enriched the material with heavy elements, and countless other factors. Our solar system formed from a specific molecular cloud in the Milky Way galaxy approximately 4.6 billion years ago. The chemistry of that cloud left its signature in every asteroid, comet, and planet we've ever studied. We know what solar system ice looks like at the molecular level. We know the ratios of different isotopes of hydrogen, carbon, nitrogen, and oxygen that characterize objects born here. But 3I Atlas comes from elsewhere. The mixture of gases in its coma and the isotopic ratios of its constituent elements could offer the first direct evidence of interstellar ice composition ever recorded. Think of it like a chemical passport. If you could analyze the molecular structure of ice from a comet born in our solar system versus one born around a different star, possibly in a different region of the galaxy with different abundances of heavy elements, you might find distinct differences. The ratio of deuterium to hydrogen, for instance, varies depending on the temperature and conditions where water ice forms. The abundance of carbon monoxide versus carbon dioxide can tell you about the temperature gradient in the protoplanetary disk, where the comet formed. Complex organic molecules, if present, might indicate the chemical richness of the parent system. Here's where things get really strange. The James Webb Space Telescope has added crucial details to the story. According to reports, JWST has detected water vapor, carbon dioxide, and other organic compounds in 3I Atlas's coma, the glowing cloud of gas that surrounds its nucleus. For context, Webb's near-infrared spectrograph is one of the most sensitive instruments ever deployed for studying the chemical composition of celestial objects. It can detect molecular fingerprints by analyzing how different molecules absorb and emit light at specific infrared wavelengths. When Webb pointed its instruments at 3I Atlas, it was looking for these signatures. Water vapor shows up as distinctive absorption lines in the infrared spectrum. So does carbon dioxide. Organic compounds, molecules containing carbon-hydrogen bonds, have their own spectroscopic signatures. The findings suggest that 3I Atlas contains volatile materials similar to those found in early solar system comets. But here's the question that emerges. If this comet formed in another star system, possibly with a different chemical composition than our own, why does it look so similar? Is comet chemistry universal, regardless of where in the galaxy you form? Or are we seeing convergent composition, where vastly different formation processes can produce similar end results? Some researchers theorize that the fundamental chemistry of planet formation might be more uniform across the galaxy than previously thought. The same physical processes that governed the condensation of ice and dust in our solar system's protoplanetary disk would operate in other systems, potentially producing similar results. But others point out that we're only seeing what's on the surface of 3I Atlas. The outer layers of an interstellar comet would have been bombarded by cosmic radiation for potentially millions of years during its journey through space. That radiation can break apart molecules, alter chemical bonds, and create new compounds that weren't present when the comet left its parent system. We might be looking at processed material, not the pristine ice from its birth system. Let me shift gears and talk about what happened to 3I Atlas during its closest approach. Yesterday, on October 29, 2025, when the comet reached perihelion at 1.356 astronomical units from the Sun, about 126 million miles, it experienced peak solar radiation levels roughly half as intense as what Earth receives. That might not sound like much, but remember, this object has spent possibly millions of years at temperatures near absolute zero in interstellar space. Suddenly heating up, even moderately, is causing dramatic changes. The process is called sublimation. Unlike melting, where a solid becomes a liquid, sublimation is when a solid converts directly to gas. On a comet, the outer layers of ice absorb solar radiation and sublimate, releasing gas molecules that flow away from the nucleus. These gas molecules carry dust particles with them, creating the visible coma and tail. The sublimating gas exerts pressure on the comet's surface, like millions of tiny rocket engines firing at once. This is why comets' tails always point away from the Sun, pushed by solar radiation pressure and the solar wind. The data from NASA shows something striking. 3I Atlas is losing mass rapidly during its solar pass. The steady decrease in brightness indicates that the comet is getting smaller, lighter, less substantial. Every moment, tons of ancient ice are transforming into vapor and escaping into space, never to return. By the time 3I Atlas exits our solar system and returns to the cold darkness between the stars, it will be a diminished version of itself, a fraction of its former mass, carrying visible scars from its brief passage through our Sun's sphere of influence. Alongside Hubble and the James Webb Space Telescope, observatories around the world are monitoring 3I Atlas in real time. According to reports, facilities in Chile, India, and Europe are contributing optical and infrared data. This is how modern astronomy works when a rare opportunity presents itself. No single observatory can maintain continuous observation of a target, and different instruments bring different capabilities. Optical telescopes can track the comet's brightness changes and the morphology of its tail. Infrared observatories can detect heat signatures and identify specific molecules through spectroscopy. Radio telescopes can sometimes detect emissions from certain molecules in cometary comas. By combining data from multiple sources, researchers are building a comprehensive, three-dimensional model of the comet's tail structure and outgassing behavior. Think of it like assembling a jigsaw puzzle where each observatory contributes different pieces. Hubble provides high-resolution images showing the dust plume and tail structure in visible light. Webb penetrates through the dust with its infrared vision to analyze the chemical composition of the gases. Ground-based observatories provide continuous monitoring that space telescopes, with their limited observation time, can't match. Together, these datasets create a more complete picture than any single instrument could provide. The three-dimensional modeling is particularly important. A comet's tail isn't a simple, straight structure. It's a complex, dynamic phenomenon influenced by the comet's rotation, the uneven distribution of ice on its surface, and the interaction between outgassing molecules and solar radiation pressure. Some regions of the nucleus might be more active than others, creating jets of material that spiral away as the comet rotates. Understanding this structure helps scientists determine where the volatile materials are located on the comet and how they're being released. Before you dismiss this as just another comet, consider what makes 3I Atlas unique in the context of interstellar visitors. The three confirmed interstellar objects we've now detected, Oumuamua, Borisov, and Atlas, each tell a different story. Oumuamua, discovered in October 2017, remains the most mysterious. It showed no visible cometary activity, no tail, no detectable coma, yet it was accelerating in a way that suggested outgassing was occurring. Its unusual elongated shape, inferred from how its brightness varied as it tumbled through space, sparked intense speculation. Some researchers proposed it might be a fragment of a planet torn apart by tidal forces, its surface altered by eons of cosmic radiation. Others suggested it could be a new class of object entirely, perhaps consisting of frozen hydrogen that would sublimate without creating visible outgassing. A few even proposed it might be artificial, a suggestion that captured public imagination but lacked evidence. Then came 2I Borisov in August 2019, discovered by amateur astronomer Gennady Borisov using his custom-built telescope in Crimea. Borisov was, in many ways, reassuringly normal. It had a visible tail. Spectroscopic analysis showed it contained water, carbon monoxide, and other volatiles familiar from solar system comets. Its behavior and composition suggested that comet formation might be a universal process, producing similar results regardless of which star system you're in. But 3I Atlas is exhibiting something different entirely. The hybrid behavior mentioned in the reports, where it has a stable hyperbolic trajectory but shows unusually intense volatile activity, places it somewhere between the inert Oumuamua and the typical Borisov. This makes it a unique case study in understanding how interstellar comets react to solar radiation. The question that emerges is this: What can 3-Eye Atlas teach us about planetary system formation in other parts of the galaxy? Consider the information encoded in this single object. The isotopic ratios in its ice can tell us about the temperature and pressure conditions in the protoplanetary disk where it formed. The presence or absence of certain molecules indicates what elements were available in that system. The comet's structure, how porous or dense it is, reflects how it accreted from smaller particles. Even the way it's breaking apart as it approaches the Sun provides clues about its internal composition and how tightly bound its materials are. Research in this field has shown that comets are not uniform bodies. They're more like loosely bound collections of smaller particles held together by weak gravitational forces and frozen ices. When you heat a comet, it doesn't melt uniformly. Different ices sublimate at different temperatures. Water ice is relatively stable and requires significant heating to sublimate. Carbon monoxide and carbon dioxide ices are more volatile and begin outgassing at much greater distances from the Sun. The sequence in which different volatiles appear in a comet's coma as it approaches the Sun tells you about the comet's layered structure. If 3-Eye Atlas formed in another star system, possibly around a star with different characteristics than our Sun, its internal structure might reflect those different formation conditions. Perhaps the temperature gradient in its birth disk was steeper or shallower than in our solar system. Perhaps the ratio of rock to ice is different. These differences, if they exist, would be encoded in observable characteristics: how quickly it's losing mass, what molecules appear first in its coma, how its brightness changes with distance from the Sun. Let's talk about what we do know from the observations. The reports indicate that observatories are combining their optical and infrared data to build a three-dimensional model of the comet's tail structure and outgassing behavior. This is more complex than it might sound. A comet's tail is not a static structure. It's constantly changing as new material sublimates from the nucleus and older material flows away into space. The gas molecules released through sublimation expand rapidly, creating the diffuse coma that can extend for tens of thousands of miles around the tiny nucleus. Meanwhile, dust particles lifted off the surface by escaping gas form their own tail, often with a slightly different shape than the gas tail because dust particles have more mass and respond differently to solar radiation pressure. By analyzing images taken over time, researchers can track how individual features in the tail move and evolve. They can identify jets of material, regions where outgassing is particularly intense. They can measure the speed at which material is escaping from the nucleus. They can even estimate the size and composition of dust particles based on how they scatter sunlight. The infrared data from Webb and other instruments adds another dimension. Infrared spectroscopy reveals what molecules are present in the gas phase. The relative abundances of different molecules can be calculated by measuring the strength of their spectroscopic signatures. If water vapor is abundant but carbon monoxide is scarce, that tells you something about the comet's composition. If complex organic molecules are detected, molecules containing carbon, hydrogen, nitrogen, and oxygen in various combinations, that's particularly interesting because these are the building blocks of biochemistry. Think about what that means for our understanding of how life's precursor molecules are distributed across the galaxy. Earth's water and organic compounds had to come from somewhere. The prevailing theory is that comets and asteroids delivered these materials to the early Earth through impacts. If every star system produces comets with similar chemistry, then the raw ingredients for life might be common throughout the galaxy, distributed by the same processes that operated in our solar system. But there's another possibility suggested by the data. The phrase, "the first direct evidence of interstellar ice composition ever recorded," is significant. Until now, everything we know about the chemistry of other star systems comes from analyzing light from distant objects. We can study the spectra of exoplanet atmospheres, detecting molecules like water vapor, methane, and carbon dioxide from hundreds of light years away. We can analyze the light from dying stars to determine their chemical composition. But these are remote observations, indirect measurements. With 3I Atlas, we have actual matter from another star system passing close enough for detailed study. It's like the difference between seeing a photograph of an exotic location versus actually visiting it. The level of detail we can obtain is fundamentally different. We can study this comet with the full arsenal of astronomical instrumentation, from visible light to infrared to potentially even radio wavelengths, gathering data that would be impossible to obtain from a distant object. One possibility suggested by the data is that the mixture of gases and isotopic ratios in 3I Atlas could confirm whether planet formation chemistry is universal or varies significantly between different regions of the galaxy. Our solar system formed from a molecular cloud in what's called the Orion Spur, a minor spiral arm of the Milky Way, about 26,000 light-years from the galactic center. The chemical composition of that cloud was influenced by previous generations of stars in our region, their supernovae enriching the interstellar medium with heavy elements. A star system that formed in a different part of the galaxy, perhaps closer to the galactic center where stellar density is higher and supernova rates are greater, or perhaps in the galactic halo where metal abundances are lower, might produce comets with measurably different chemistry. If 3I Atlas's chemistry closely matches solar system comets, that would suggest planet formation is a robust process that produces similar results across a wide range of conditions. But if it shows significant differences, that would tell us that local conditions matter more than we thought. Another interpretation focuses on what the observations reveal about the comet's origin system. By working backward from the comet's current trajectory, astronomers can potentially identify which direction in the sky it came from. Its velocity of 58 kilometers per second relative to the Sun, combined with the Sun's own motion through the galaxy, gives us information about the relative motion between 3I Atlas's parent system and our own. However, the comet has likely been traveling for so long that its parent star could be anywhere along that trajectory, and the motion of stars through the galaxy means that a star in that direction now might have been in a completely different location when the comet was ejected. A third possibility is more speculative but intriguing. Some researchers have proposed that the intense outgassing activity of 3I Atlas, despite its long journey through interstellar space, might indicate it was ejected relatively recently from its parent system, perhaps only a few million years ago rather than tens or hundreds of millions of years ago. The reasoning goes like this. Cosmic radiation in interstellar space breaks apart molecules on a comet's surface, creating a radiation-processed crust that's more stable and less volatile than pristine ice. An old interstellar comet would have a thick crust and show relatively little outgassing when heated. But if 3I Atlas is showing intense outgassing, maybe its surface hasn't been heavily processed yet, suggesting a shorter journey time. However, this interpretation has problems. The thickness of the radiation crust depends not just on time, but on the radiation environment the comet passed through during its journey. If it traveled through regions of space with lower cosmic ray flux, perhaps by chance avoiding the densest parts of the galactic disk, it might retain more volatile material even after a long journey. Additionally, the impact of even a tiny interstellar dust grain hitting the comet at high velocity during its journey could excavate fresh ice from below the crust, exposing volatile material that would then respond vigorously to solar heating. Here's another piece of the puzzle. The fact that 3I Atlas was discovered at all is itself significant. Remember, it was first detected on July 1, 2025, at a distance of 4.5 astronomical units from the Sun, just inside Jupiter's orbit. That's quite far from the Sun, and comets at that distance are typically faint. The fact that Atlas, an automated survey designed primarily to detect potentially hazardous near-Earth asteroids, spotted 3I Atlas suggests the comet was already showing some activity, already bright enough to be noticeable. Most comets from the outer solar system don't begin significant outgassing until they're much closer to the Sun, inside the orbit of Mars, at around 1.5 astronomical units. If 3I Atlas was active at 4.5 AU, that implies it contains particularly volatile ices, perhaps carbon monoxide or nitrogen ices that sublimate at lower temperatures than water ice. This early activity is consistent with the reports of unusually intense volatile behavior. It suggests that 3I Atlas is not a typical comet in terms of its composition or structure, even compared to other comets we've studied. Whether this reflects something unusual about the comet itself or about conditions in its parent system remains an open question. The research teams analyzing the data will be looking for any subtle differences in isotopic ratios or molecular abundances that might provide clues. The ratio of deuterium to hydrogen in the comet's water, for instance, is something that can be measured spectroscopically and compared to the values found in solar system comets. The abundance of carbon monoxide relative to water is another diagnostic. The presence of more complex organic molecules, if any are detected, would be particularly interesting because it would tell us whether the chemistry that produces these molecules operates the same way in other star systems. The controversial angle in this discovery, if there is one, lies in the interpretation of what 3I Atlas's chemistry tells us. Some researchers might argue that the similarity between interstellar comet compositions and solar system comets, assuming the similarity is confirmed by detailed analysis, indicates that planet formation is a universal process with predictable outcomes. This would support the idea that the chemical building blocks of life are widely distributed throughout the galaxy, wherever planets form. Others might caution that we're seeing only the outer layers of the comet, material that's been processed by eons of cosmic radiation, and that the pristine interior composition might be quite different from what we're measuring in the coma. There's also an ongoing discussion in the scientific community about how to interpret the outgassing behavior of interstellar objects. With Oumuamua, the detection of non-gravitational acceleration that couldn't be explained by the Sun's gravity alone, sparked intense debate. Some attributed it to outgassing, even though no coma was detected. Others proposed more exotic explanations. With 3I Atlas, we have clear evidence of outgassing, but the question is whether the intensity and characteristics of that outgassing are consistent with what we'd expect for an object that formed in another star system. If the behavior is indistinguishable from solar system comets, what does that tell us? If there are subtle differences, how should we interpret them? As 3I Atlas continues its journey away from the inner solar system, scientists are racing against time to capture as much data as possible before it fades beyond detection. Yesterday's Perihelion passage on October 29, 2025, represented the moment of maximum scientific opportunity. At its closest approach to the Sun, the comet experienced the most intense solar radiation of its current journey, and its outgassing reached peak levels. The most detailed spectroscopic measurements were obtained during those critical hours because the coma was at its brightest and contained the highest concentrations of gas molecules. Now, as 3I Atlas begins its outbound journey, it has already started to fade as it moves away from the Sun and its outgassing decreases. By the time it reaches Jupiter's orbit again on its way out of the solar system, it will likely be too faint for detailed study. Within a few years, it will cross the outer boundary of the solar system and return to interstellar space, becoming once again a dark, frozen wanderer in the vast distances between stars. The data collected during this brief observing window will be analyzed for years to come, squeezed for every bit of information about this messenger from an alien star system. The event could reshape our understanding of how icy bodies form and evolve in alien star systems. If the detailed analysis reveals significant chemical differences between 3I Atlas and solar system comets, it would confirm that local conditions in a star system leave detectable fingerprints on the objects that form there. We could potentially use those fingerprints to infer properties of the parent system. Was it metal-rich or metal-poor? Was it near regions of active star formation? What was the temperature structure of its protoplanetary disk? The practical implications of this research extend beyond pure scientific curiosity. Understanding the composition and behavior of interstellar objects has relevance for planetary defense. While the probability is extremely low, it's theoretically possible for an interstellar interloper to collide with Earth. Knowing how these objects behave, how they respond to solar heating, and what they're made of could inform strategies for deflecting or disrupting them if one were ever found to be on a collision course. More broadly, the study of interstellar objects tells us about the galaxy we inhabit. The number of interstellar objects passing through our solar system at any given time depends on how many objects are drifting through interstellar space, which in turn depends on how efficient planetary systems are at ejecting objects during their formation. By studying the properties of the interstellar objects we detect, we learn about the typical outcomes of planet formation across a wider sample of star systems than we could ever hope to visit. There's also the question of whether such objects might have once carried life-building molecules across the cosmos. This idea, called Panspermia, proposes that life's ingredients, or perhaps even life itself in the form of hardy microorganisms, could be distributed between star systems via comets and asteroids. While this remains speculative, the detection of complex organic molecules in interstellar comets would lend some support to the idea that the chemistry of life is not unique to Earth, but might be widespread in the galaxy. Let's bring this back to this moment. Right now, as you read this, 3I Atlas is racing away from Perihelion at more than 36 miles per second. Every hour it travels more than 130,000 miles farther from the Sun. Yesterday, at its closest approach, it experienced peak heating and outgassing. Today, the intensity is already diminishing. Its nucleus, probably only a few miles across, is still sublimating away, though at a decreasing rate as it moves to colder regions of space. The gas and dust streaming off its surface are creating a tail that stretches for millions of miles behind it, a visible marker of its passage through our solar system. Telescopes on 3 continents and in orbit around Earth are pointed at this tiny speck of ice and rock, capturing photons that have bounced off its surface or been emitted by molecules in its coma. Those photons are being analyzed, their wavelengths measured to extraordinary precision, each measurement contributing to our growing understanding of what this object is and where it came from. The scientists studying 3I Atlas are faced with a problem that's simultaneously frustrating and exhilarating. They have access to actual matter from another star system, a sample of extrasolar material delivered to our doorstep by chance, but they can only study it remotely, through telescopes, for a brief window of time before it fades from view. They can't send a spacecraft to rendezvous with it. Its speed and trajectory make that impossible with current technology. They can't capture a physical sample to bring back to Earth for laboratory analysis. They're limited to analyzing the light it reflects and emits, extracting as much information as possible from spectroscopic signatures and photometric measurements. Yet from this limited data, they're attempting to reconstruct the comet's composition, its structure, its history, and the characteristics of the star system where it formed. It's like trying to write the biography of a stranger based solely on a photograph and a brief glimpse of their shadow. And yet, this is how astronomy has always worked. We study the universe through the light it sends us, reading messages encoded in photons that have traveled across unimaginable distances to reach our instruments. The difference now is that with instruments like the James Webb Space Telescope and the Hubble Space Telescope, we can read those messages with unprecedented clarity. We can detect molecules that would have been invisible to earlier generations of telescopes. We can measure isotopic ratios that reveal the thermal history of materials. We can track subtle changes in brightness and color that tell us about outgassing patterns and dust production. The question that no one can fully answer yet is what the complete analysis of 3I Atlas will reveal. Will it confirm that comets everywhere are fundamentally similar, products of a universal set of physical and chemical processes? Will it show us something unexpected? Some signature that speaks of formation conditions radically different from those in our solar system? Will we detect molecules we've never seen before, combinations of elements that don't occur in solar system comets? The preliminary data, with its detection of water vapor, carbon dioxide, and organic compounds, suggests similarity rather than radical difference. But the detailed analysis, comparing precise isotopic ratios and molecular abundances, might reveal subtle variations that tell a more complex story. For context, when we talk about isotopic ratios, we're referring to the relative abundances of different isotopes of the same element. Hydrogen has two stable isotopes, normal hydrogen with one proton and one neutron called deuterium. The ratio of deuterium to hydrogen in water ice depends on the temperature and conditions where that ice formed. Solar system comets show a range of deuterium to hydrogen ratios, and by measuring these ratios in 3I Atlas, scientists can compare it to the known distribution from solar system objects. Similarly, oxygen has three stable isotopes: oxygen-16, oxygen-17, and oxygen-18, and their relative abundances can vary depending on formation conditions. Carbon, nitrogen, sulfur, each of these elements has isotopes whose ratios can provide clues about origin and history. The challenge is that measuring these ratios from remote spectroscopy is extraordinarily difficult. It requires high-resolution spectra with excellent signal-to-noise ratios, and even then, the measurements come with significant uncertainties. The research teams working on 3I Atlas will be pushing their instruments and analysis techniques to the limit to extract this information. They'll be developing new models to interpret the data, comparing their observations to theoretical predictions for how comets should behave under different formation scenarios. They'll be writing papers that will be scrutinized by peer reviewers and debated at conferences. And in the end, the results will add one more data point to our growing knowledge of what exists beyond our solar system. Here's where another dimension of mystery enters. The reports mention that 3I Atlas exhibits hybrid behavior, with a stable trajectory, but unusually intense, volatile activity. Let's unpack what makes this strange. A stable hyperbolic trajectory means the comet's path through the solar system is well-defined and predictable. It's not tumbling chaotically. It's not undergoing dramatic changes in direction. The gravitational influences of the Sun and planets on its motion can be calculated with precision, yet its outgassing is unusually intense, intense enough to create the brilliant dust plume and extended tail captured by Hubble. Here's the question: where is all that volatile material coming from? One possibility is that 3I Atlas is simply more ice-rich than typical solar system comets. Perhaps in its parent system, the region where it formed had more water and volatile ices relative to rock and dust. This could occur if the comet formed in the outer regions of its birth disk, far from the parent star where temperatures were low enough for even the most volatile compounds to condense. Another possibility is that 3I Atlas has a particularly porous structure, with lots of empty space between loosely bound particles. This would give it a high surface area to volume ratio, meaning more of its interior is in contact with solar radiation, leading to more extensive outgassing than a denser comet of the same size. A third possibility is more intriguing. Perhaps the comet is fragmenting as it approaches the Sun. The intense thermal stress of rapid heating, combined with the mechanical stress from gas pressure building up beneath the surface as ices sublimate, could cause the nucleus to crack or break apart. This has been observed in solar system comets before. Comet Shoemaker-Levy 9 famously broke into multiple fragments before colliding with Jupiter in 1994. More recently, Comet 2I Borisov showed evidence of fragmentation during its passage through the inner solar system. If 3I Atlas is fragmenting, each fragment would present fresh surface area to solar radiation, dramatically increasing the total outgassing rate. The reports mention that NASA's data shows a steady decrease in the comet's overall brightness, which is consistent with it losing mass rapidly. But brightness changes can be complex to interpret. A decrease in brightness could mean the comet is simply getting smaller as it loses mass. Or it could mean that the most volatile materials on the surface have been exhausted, and now we're seeing deeper layers that are less active. Or it could indicate fragmentation, with pieces breaking off and dispersing. Distinguishing between these scenarios requires careful analysis of how the brightness changes correlate with distance from the Sun, how the color of the comet changes as different ices sublimate, and whether the morphology of the tail shows any signs of multiple emission sources. The fact that observatories worldwide are building a three-dimensional model of the tail structure suggests they're looking for exactly these kinds of clues. If the tail shows evidence of multiple jets or streams of material, that could indicate either active regions on the nucleus or perhaps fragmentation. The shape of the tail can also tell us about the size distribution of dust particles being released. Large particles, with more mass, are less affected by solar radiation pressure and tend to curve more gently behind the comet. Fine dust particles are pushed more strongly and create straighter, more extended tails. By analyzing the brightness and color of different parts of the tail, researchers can infer what sizes of particles are present and in what proportions. This, in turn, tells them something about the physical structure of the nucleus. Is it crumbly, breaking apart into dust easily? Or is it more cohesive, requiring significant stress to release material? These questions matter because they relate to how the comet formed and how it has evolved during its long journey through interstellar space. A comet that formed through gentle accumulation of small ice particles in a protoplanetary disk would have a different structure than one that formed through the violent collision and reaggregation of larger bodies. The way it breaks apart under thermal stress reflects that formation history. But let's step back and consider the deeper question this raises. We're watching an object die in real time, an object that has existed for potentially millions or billions of years, and its death is being caused by an encounter with our Sun, a star it was never meant to meet. There's something almost poignant about that. This comet formed in orbit around another star, perhaps was part of that system's equivalent of the Kuiper belt, a reservoir of icy bodies beyond the planets. At some point, gravitational interactions, perhaps the migration of a giant planet or a close encounter with a passing star, perturbed its orbit. It was thrown outward, escaping its parent star's gravitational pull, and began drifting through interstellar space. For millions of years it traveled through the cold darkness between stars, a frozen time capsule carrying ice and dust from its birth system. Then, by sheer chance, its trajectory brought it close to our solar system. The Sun's gravity bent its path, pulling it inward, and now, for this brief moment, it's illuminated, visible, studied, its secrets being teased out by the instruments we've built to understand the universe. In a few months, it will fade from view, exit our solar system, and return to interstellar space, diminished by its passage, forever changed by its encounter with our Sun. It will drift for eons more, perhaps eventually passing near another star, or perhaps traveling the galaxy for billions of years without another close encounter. We'll never know its ultimate fate, but for this moment, it's ours to study, a gift from the cosmos, a sample of stellar systems beyond our reach. The scientific value of this event cannot be overstated. With only 3 confirmed interstellar objects detected so far, each one dramatically expands our knowledge. Oumuamua showed us that interstellar objects exist and can have properties we don't fully understand. Borisov showed us that at least some interstellar comets are similar to solar system comets, suggesting universal planet formation processes. Now, 3I Atlas is showing us something in between, an object that shares some characteristics with solar system comets, but displays unusual intensity in its outgassing. This diversity is itself a valuable data point. It suggests that interstellar objects, like solar system objects, come in varieties. There isn't a single template for what an interstellar comet should look like or how it should behave. They're individuals, shaped by their particular formation histories and subsequent experiences. As our detection capabilities improve, we'll likely discover more interstellar visitors. The Vera C. Rubin Observatory, scheduled to begin operations soon, will survey the entire visible sky repeatedly, detecting faint objects that previous surveys would miss. Researchers predict it could detect a couple of interstellar objects per month once it's fully operational. With a larger sample size, we'll be able to look for patterns and draw more robust conclusions about the population of objects drifting through the galaxy. Let's return one more time to what makes 3I Atlas scientifically precious. The phrase, "the first direct evidence of interstellar ice composition ever recorded," captures the essence of why this matters. Until now, our understanding of chemistry in other star systems has been built from remote sensing. We observe exoplanets transiting their parent stars and analyze how starlight filters through their atmospheres, revealing molecular signatures. We study emission lines in the spectra of distant nebulae where stars are forming. We analyze light from galaxies billions of light years away. But these are all indirect measurements of remote objects. 3I Atlas is different. It's here, in our solar system, close enough for detailed study with our best instruments. The molecules we're detecting in its coma were frozen into ice in another star system. The isotopic ratios we're measuring reflect conditions in that system's protoplanetary disk. This is the closest we can come to having a sample return mission from another star system without actually sending a spacecraft there. And that's an achievement worth celebrating, because with current technology, sending a probe to even the nearest star system would take tens of thousands of years. Interstellar travel at anything approaching useful speeds remains firmly in the realm of science fiction, but interstellar comets bring samples to us, delivered by the patient workings of gravitational dynamics operating over millions of years. The researchers analyzing 3I Atlas will be comparing their findings to models of planet formation developed over decades of studying our own solar system. These models describe how protoplanetary disks, the swirling clouds of gas and dust that surround young stars, gradually condense into planets, asteroids, and comets. The temperature gradient in the disk, decreasing with distance from the star, determines what materials can condense where. Close to the star, only refractory materials like rock and metal can survive in solid form. Farther out, beyond what's called the snowline, water ice can condense. Even farther out, more volatile ices like carbon monoxide and methane can freeze. The chemical composition of objects in a planetary system reflects where they formed in that temperature gradient. By analyzing 3I Atlas's composition, scientists can attempt to infer where in its parent system's protoplanetary disk it formed. If it's rich in highly volatile ices, it likely formed in the cold outer regions. If it's primarily water ice with smaller amounts of other volatiles, it might have formed closer in. These inferences are complicated by the fact that objects can migrate after formation and by the modifications that occur during millions of years in interstellar space, but the fundamental composition still carries information about origin. One of the most tantalizing questions is whether 3I Atlas contains complex organic molecules, the carbon-based compounds that serve as the building blocks for life as we know it. The term organic compounds in the reports could refer to anything from simple molecules like methane and methanol to more complex molecules like formaldehyde, ethanol, or even amino acids. The James Webb Space Telescope's spectroscopic capabilities include the ability to detect some of these molecules if they're present in sufficient abundance in the coma. The detection of complex organics would be significant because it would indicate that the chemistry leading to these molecules operates in other star systems. On Earth, many organic molecules important for life are thought to have been delivered by comets and asteroids during the planet's early history. If similar molecules are found in an interstellar comet, it strengthens the case that the chemical precursors to life might be common throughout the galaxy. However, it's important to note that organic in this context doesn't mean biological. Organic molecules can form through purely chemical processes without any involvement of life. They're found in interstellar clouds, in meteorites, in comets, in the atmospheres of planets and moons. The presence of organic molecules tells us about chemistry, not biology. But it does tell us that the same chemistry operates across the galaxy, which has implications for our understanding of how life might arise elsewhere. As we move past October 29, 2025, the date of Perihelion, the window for intense scientific observation is now shifting from observation to analysis. Yesterday was the moment everyone had been waiting for, when 3I Atlas was at its brightest, when the outgassing was most vigorous, when the chemical signatures were strongest. Telescope time on major observatories was precious and highly competitive, and facilities around the world dedicated their instruments to observe 3I Atlas at the critical moment. Now, as the comet begins its outbound journey, it is fading rapidly. The window for detailed observation is brief, a matter of weeks or months at most. Then 3I Atlas will return to the darkness, and we'll be left with whatever data we managed to collect during its passage. This data will be archived, made available to researchers worldwide, analyzed and reanalyzed for years to come. Future generations of scientists might develop new techniques for extracting information from these observations, finding clues that we miss with current methods. The data from 3I Atlas will outlive those who collect it, a lasting contribution to our knowledge of the cosmos. Let me step back and offer a final reflection on what this all means. We live in an era where, for the first time in human history, we can detect and study objects that formed around other stars. That's an extraordinary capability. For all of human existence until October 2017, we had never confirmed the detection of an interstellar object passing through our solar system. Now, just 8 years later, we've detected 3, and we're studying the third one with instruments that represent the cutting edge of astronomical technology. The pace of discovery is accelerating. Our ability to understand what we observe is growing. And the implications are profound. We're learning that the galaxy is a dynamic place, with matter constantly being exchanged between star systems. We're learning that planet formation, while following universal physical laws, produces diverse outcomes. We're learning that the chemistry we observe in our solar system is not unique, but may be representative of what occurs throughout the galaxy. And we're learning to ask better questions. Each interstellar object we detect raises new questions even as it answers old ones. Why does 3I Atlas outgas so intensely? Where exactly did it come from? How long has it been traveling through interstellar space? What was its parent system like? Did planets form there? Does life exist there? We may never know the answers to all these questions, but the act of asking them, of reaching toward understanding, is what drives science forward. The story of 3I Atlas is ultimately a story about perspective. From the comet's point of view, if we can anthropomorphize for a moment, our sun is just another star, one of hundreds of billions in the galaxy, a chance encounter during an eons-long journey through space. The comet has no awareness of the excitement it's causing among the intelligent species inhabiting the third planet of this particular star. It's simply following the laws of physics, responding to gravitational forces and solar radiation according to its composition and structure. But from our perspective, this comet is a marvel, a messenger from the distant reaches of the galaxy, a sample of conditions we can never directly visit, a teacher showing us how the universe works beyond our immediate cosmic neighborhood. The contrast between these perspectives highlights something fundamental about science. We create meaning through observation and understanding. The universe doesn't care whether we study it or not. Comets will outgas, stars will shine, galaxies will collide whether or not anyone is watching, but we do watch, and in watching we understand, and in understanding we find our place in the cosmos. 3I Atlas will soon fade from our view, continuing its journey through the galaxy. But the knowledge we gain from studying it will remain, integrated into our growing understanding of how the universe works, a small but significant piece of the vast puzzle of cosmic history. And that, in the end, is the real legacy of this frozen visitor from beyond our solar system.